let's continue with this operational amplifier. So we had seen the case of a non-inverting amplifier where the inverting input is connected to a ground terminal through this resistor R1, and the output of this amplifier in a closed loop system was fed back to the inverting input through the resistor RF. And to the positive input terminal of the operational amplifier, we connected the voltage source named as VI, and we know that this node terminal was called as V2, this node terminal was called as V1, and the difference between these two is termed as VID. And since operational amplifier in the open loop has infinite input resistance, so we say that no current can flow inside the operational amplifier terminals, whether it's positive or negative. So IP is the I positive, that is 0, and here we can say that this current IN, which is trying to enter the negative input terminal, is also 0. So this is because in the open loop Ri is infinite. Okay, this is in the open loop configuration. So when there is no feedback, so that's the property of ideal operational amplifier. But now this is the case for the operational amplifier with the feedback, where there is a feedback from the output, portion of output is fed back to the input. So in this case, we are to determine the Ri, which is RIF, which is the resistance, input resistance with the feedback, when the feedback is applied. All right, so obviously resistance is the ratio of voltage divided by current. Voltage applied is VI right over here. Okay, and the current is, we've seen that this current IP is equal to 0, because there is due to ideal characteristics, no current can enter through the positive terminal. So we say that input resistance for the closed loop is infinity. Okay, with the feedback. Similarly, for the output resistance, which is right over here, so this voltage, output voltage of the operational amplifier serves as an ideal voltage source, which can be connected to the load over here. Okay, so we see that here there is no resistance, and the all voltage VO appears across the load resistance RL. So therefore the ROF can be written as this ROF is 0. So these are the ideal characteristics for the amplifier with feedback. Okay, obviously when we see that this in a practical case, these values are not going to meet, that means the ideal characteristics that we have seen here, whether it's open loop or closed loop, they are not going to be what we provided here. Okay, so just to summarize, we see that for the inverting amplifier, just if we take a look at the inverting amplifier, where the input signal is applied to this negative input terminal through this resistor R1, and we have this output right here, and positive is connected to the ground, and therefore this current is I1. Okay, and RIF could be V over I, which is VI over, this is the input current that we see that. But now there is a current flowing through the resistance, the current trying to enter the operational amplifier, that is IP and IN, they are 0. Okay, IP IN is equal to 0, but this current is flowing because of the source resistance. So this current can be represented as VI divided by VI by R1. So the resistance would be R1 for the closed loop. Again, this is the ideal value. This is the exact value right over here. And ROF, that is with the feedback. Again, this output voltage of the operation amplifier will behave like this, as we've seen that, and the whole voltage, the load that will connect, the voltage will appear across this load. So RF will be 0. Okay. So summary would be, this is the inverting case. And this is the non-inverting case. So RIF and ROF. These are the two values that we've seen here. F, that's the inverting, is the value of R1. ROF would be 0. And for the non-inverting, this is infinity and this is 0. Similarly, the gain, which is the closed loop gain or gain with the feedback, is defined as minus R1, RF over R1. Negative sign indicates is the inverting. The output is in 180-degree phase shift with respect to input, and the gain for this is the non-inverting case is 1 plus RF over R1. So these are the values that we've seen. So now let us take a look at the special case of the non-inverting amplifier. So we draw this non-inverting amplifier, but so we have this input which is connected to the positive input terminal, and the resistor R1 that we draw here, the resistor RF. This is the case that we have, R1 and RF. So what we do is the R1 is made short-circuited, and RF is R1 is made a open circuit and RF made a short circuit. So when it is open, that means it is infinite, and it is short, it means it is 0. So this circuit will take the form like this. We have this amplifier, and again the source VI is connected and R1 is made open now, and RF is shorted. So we have output voltage connected back to the input. And obviously we see that this is V2, and the voltage at this node, or basically VO, is fed back. So this V1. So V2 is nothing but VI, and V1 is nothing but VO. Okay. And VID would be V2 minus V1. So it would be VI minus VO. That is the difference voltage. Okay. And we'll see that V2 is the node voltage V1 due to virtual ground is equal to VI actually. So we put this value VID, which is VI minus VI, and that comes out to be 0. And this is possible because of the infinite gain of the operational amplifier. Okay, so in other words, we say that this voltage comes over here. The V2 is equal to V1, Okay, and therefore this Vi comes over here, and V1 is equal to VO. So therefore we see that VO is nothing but Vi. Okay, and the small signal model equivalent circuit for this amplifier can be represented like this. We have this input voltage, which is Vi connected between the two terminals, and we have this source, again the dependent source, positive, negative, the gain times Vi. So it's like, let's say, the gain times Vi, which is the output voltage, positive and the negative, and this is our output voltage right over here. This is ground. Okay, so we've seen that for this circuit, the output is essentially equal to 1, right? So output follows the input. So the gain in this case is 1. And therefore, we see that VO is equal to A times Vi, which is equal to Vi, and the gain is 1 here. Okay, if we make this use of this configuration, if we connect back the resistor R1 and RF, then in this case, this VO would be A times Vi, and 1 plus RF over R1 times Vi would be the amplifier. So this is the expression, non-inverting amplifier. And this is the expression for non-inverting voltage follower. Okay. So that's how this circuit is termed as voltage follower circuit. Because we see that the output voltage follows the input voltage. VO equals Vi. When we have this configuration, that output is fed back to the inverting input, and the signal input is applied to the positive terminal of the operational amplifier. Let's have an example for the non-inverting amplifier. So there is a 1K, there is a 2K, there is a 3 kilo ohm, and let's say signal input V1, signal input, this is V2, and we have an output, portion of output is fed back to the input through this resistor, having a value of about 9 kilo ohm. So we are asked to obtain the expression for the output voltage of this configuration. So how to do that? We can use the superposition principle. Okay. So what we do here, superposition, it means we make the circuit work by applying the one voltage source or one signal source at a time. And when one of them is active, the other one is disabled. So how to do that? So for the case 1, what we do here, we apply the circuit. We draw the circuit like this. Again, we have 1 kilo ohm, and this resistor is 9 kilo ohm, and the positive input is supplied with, let's say, 2 kilo ohm, and V1 is active, whereas you have this resistance 3 kilo ohm. So let's draw it like this. However, this V2 is made 0. So it is basically connected to the ground. So we'll see that this is connected to the ground. Okay, and the output that we have now, let's call it VO1. So expression for the VO1 would be, we come back, the node voltage here is V2, here is V1. So let's obtain the expression for the VO2 first. V2, we see here the V2 can be obtained by the voltage division rule. So it is 3 into V1 divided by 2 plus 3. So it is 3V1 by 5. And therefore, the resultant output voltage would be, again, by the principle of by the closed loop feedback gain. We know that for the non-inverting, it is 1 plus 9 by 1. So it is, we see that for the closed loop, 1 plus Rf over R1 times Vi. So this is Rf actually, and this is R1 right over here, and multiplied by V2, because this is the input voltage that is applied to the positive input terminal. And therefore, we see that here 10 times 3V1 divided by 5. So it is 6V1. Okay, so that's the output voltage when only V1 is active. Similarly, we now have V1 shorted and V2 active. So let's draw the case. So you see here R1 is 1 kilo ohm as usual. We have this is 1K. This is 9K. This is ground. And V1 is made 0 now. So it's essentially connected to the ground. It has a value of 2K, and we have this 3K, and V2 is applied to the source. And the output voltage that is to be determined is VO2. Okay. So again, we have the node V2 and we have the node V1. So how to understand this? So is basically we see that this is ground and this is 2 kilo ohm. This is 3K. And here is the V2 and the node. This is the voltage source V2 actually, right? And this V2 is different than this V2. So let's say this is small V2s and V1, and these are capital V2 and V1s right here. So this is V2. So V2 can be written as total output voltage will write. So again, 1 plus 9 by 1, this is the gain set by the resistors, and multiplied by the V2, which can be written as 10, and value of V2 can be obtained as 2 into V2 divided by 2 plus 3. So it's 20 by 4 times V2. So the total voltage VO would be VO1 plus VO2, and this is 6 times. We see that VO1 is this one, 6V1 plus 4V2. So that's the expression for the complete circuitry. Okay, what if we have this, let's say, the source, the resistance that was shorted here, instead we apply another voltage source to this one. That was 1 kilo ohm VO. It's 9K, that was 2K. Let's say it is 3K. Here is the V2, here is the V1. And how to obtain the expression for this circuitry. So again, the node here V2 and the node voltage here is V1. So again, we can apply the U superposition to obtain this. So obtain the response of VA1, which is due to V1 present alone. Obtain the response of VO2 due to V2 present alone, and obtain the response due to V3 present alone. And then final output would be the sum of all the voltages that we have seen here. So this can be left as an exercise. Okay. Let's say we are asked to design a non-inverting amplifier. Positive. And R1 and RF values are to be determined. So what is asked here is a design this amplifier with a gain of 2. So when for the output voltage of 10 volt, for the maximum output voltage of 10 volt, the current in the voltage divider is to be 10 microampere. So first of all, we see that the expression, from the expression, the amplifier can be designed like this: 1 plus RF over R1 times VI. That's the output expression. And what we need a gain. So that's how this has to be a gain, which is the gain times VI. So gain has to be a 2. So this ratio, this quantity 1 plus RF over R1 has to be equal to 2. Okay. And another, for the maximum 10 volt output, VO is given. VO is 10 volt max. The current through the voltage divider. The voltage divider is, if we see here, right over here. So this is basically a voltage divider. Okay, so we can draw it here. Let's say this is VO, this is RF, this is grounded, and this is R1. And what we have here is the node V1. This is V2. So it says that the current has to be 10 microampere for a VO equal to 10 volt max. So we know that what would be the value of RF and R1. This is the value we have to determine. So how to do that? We know that the current is given and the voltage is given. So RF plus R1 can be VO divided by I, which is 10 divided by 10 microampere, which is 1 mega ohm. So we choose that RF equals to R1 is equal to 0.5 mega ohm. So with these values put in here, we make sure that the maximum output voltage of 10 volt, the current is limited to the value of 10 microampere. Okay, this is how the amplifier can be designed. All right. So what is the use of voltage follower? Let's say we have a transducer which can be modeled by a voltage source Vi. It has a value of 1 volt and it has a very high source impedance of 1 mega ohm, and we connect it to the load which is having a low value of, let's say, about 1 kilo ohm. So what is the voltage delivered to the load? VL would be RL times VI divided by RL plus RS. This is RS actually. So we see here, we plug in the value 1K times 1 volt, the 1K plus 1 mega. So we see here the VL is only a fraction of VI. Okay, it drops, VL drops actually because this denominator having a large value. But what if we have this voltage source? Again, the transducer is modeled by a voltage source, or let's say transducer provides a 1 volt output and it has a high source impedance of 1 mega ohm. And before feeding it to the load, this is the load RL, we connect it to the buffer or a voltage amplifier. So with a gain of 1. Positive. Let's draw it properly. This is how we connect it. That's the RL 1 kilo ohm. So we know that what are the properties of this circuit right over here. You see here, this is the source and this is the load side. And this is the buffering, or say buffer amplifier, which has a gain of, let's say, 1. So it's a case of non-inverting connected in this. It acts as a voltage follower. So the output voltage here follows the voltage that comes here, that is VO equals to, without degradation. Okay, because this buffer provides the input resistance having a value of infinity and output resistance having a value of 0. So we've seen that. Why it provides so? Because this voltage, we know that no current can go inside the operational amplifier terminal. Therefore, it offers the value of input resistance to be infinity. And at the output, it acts as an ideal voltage source. Therefore, it gives the value RO equal to 0. So that's how we can have such configuration. And we see that we have this kind of representation. For the equivalent model, we have this voltage source, this the transducer of 1 volt, and we have this 1 mega ohm, and let's say the amplifier receives this input. This is Vi, okay, or let's say this is Vs actually. Let's say Vs, that's the source voltage from the transducer. So that's the amplifier voltage Vi. And at the output side of the amplifier, we have gain times Vi. The gain is actually 1, so that is 1. And load is connected right over here. All right, so that's how we understand these concepts.